Do you want to learn about the recent scientific results on gravitational waves and how is it connected to Eötvös Loránd University? Then tune in. We will begin soon. Welcome everyone, this is the podcast of the Faculty of Science of Eötvös Loránd University, and today is all about gravitational waves. My name is Eszter Papp, I am a PhD student in physics, and my guests are for today Professor Zsolt Frei, who is the leader of the Extragalactic Astrophysics Research Group, and Dr. Timothy Pennucci, who is a postdoctoral researcher at Zsolt Frei's research group. Greetings for you.
Hello.
Hello everyone.
After 15 years of pulsar observation, the nanograph, which is short for North American Nanohertz Observatory for Gravitational Waves, has found the first evidence for low-frequency gravitational waves permeating the cosmos. Before going into details, let's talk about gravitational waves in general. What are they?
Yeah, so gravitational waves are essentially ripples in the fabric of space-time. So Albert Einstein kind of did a number of major things in physics, right? But one of the first things he did was to unify space and time into sort of one object, into one thing that physicists could kind of measure things upon. But the second thing was a theory of gravity, which made this fabric of space-time sort of a player in the universe. So not just the stage on which things unfold, but itself a medium for information transfer. And gravitational waves are basically the way that gravity propagates, but also a way that ripples in space-time. It's effectively ripples in space-time.
How do they appear?
How do they appear? So there are a number of ways to detect gravitational waves. And so one of the ways is the ways in which nanograv has detected these gravitational waves, but they effectively are stretching and squeezing of space-time. So
how they appear, perhaps you are asking about the sources, what creates them in the universe. So Tim would like to perhaps elaborate on that?
Yeah, sure. So in order for gravitational waves to be produced, you need very compact, very dense objects to move in accelerated fashions. And you need extreme such sources, aka black holes is one very common source of gravitational waves. And for nanograv, the black holes that we are detecting effectively are supermassive black holes. So these are black holes that are millions or even billions or even tens of billions of times the mass of the sun.
Okay.
I want to re-emphasize what Tim just said, that you need the strongest gravity to create gravitational waves. So you need something which is very heavy, relatively compact, and accelerates. And if you think about a pair of black holes, not just a single black hole, but two black holes orbiting around each other, from high school physics, we know that a circular motion is basically an accelerating motion, since the vector quantity has a direction, and if you move in a circular motion, it constantly changes. So this is actually an accelerating motion. And if you look in the universe, all around, all possible astrophysical sources, you will find out that compact black holes are the most massive, smallest, and fastest accelerating sources of gravitational waves. And anything can create gravitational waves. If I wave my fist like this, it's an accelerating body of mass. We calculated that this is like 46 orders of magnitude smaller gravitational wave than we can currently detect, but everything creates gravitational waves. So if you tally all the astrophysical sources, compact binary objects, compact black holes, neutron stars orbiting around each other, perhaps a supernova exploding, throwing out mass into space in different directions, not totally uniformly. These all could be possible sources, but currently we were successful detecting gravitational waves mainly from orbiting pairs of binary black holes.
Tim, you mentioned that this is like space-time is squeezed and stretched. What does it mean? How can we imagine it?
Well, it can be hard to imagine, actually, but a very common sort of visualization is, let's say, if you have a rubber sheet or some kind of stretchy two-dimensional fabric, and on that you can place bowling balls or some other objects. And as they move about, they deform that sheet. And you can imagine if they were to move around quite quickly, then you might excite the sheet on which they rest, and that might that oscillation might propagate across the whole sheet. And in that way, you can sort of get a sense of gravitational waves as they propagate across actually the four-dimensional space-time of the universe.
I think we discussed gravitational waves in general properly, but let's go into the details of detection. How did researchers detect gravitational waves first?
So the first detection came from LIGO, which is the Laser Interferometer Gravitational Wave Observatory in the US, of which we are part of, our group in Budapest at Eötvös University. And this is a so-called direct detection. We have an interferometer with large arms, and as this Tim described, this ripple comes through the fabric of space-time. One arm gets a bit shorter, the other elongates a little bit, stretches, and therefore the interferometer itself gives a signal with the same frequency as the gravitational wave. And if you have several of these detectors, as we do, with the time delay folded in, you can triangulate the location of the object on the sky. So we kind of know which source, which galaxy at least, provided this gravitational wave and how it propagated, how much time it took, and what were the sizes of the two objects orbiting around each other. It's a completely different detection than what we are talking about right now.
Yes, because in this recent study, you used pulsars as gravitational wave detectors. How is it possible, and why was it necessary?
Yes, so let me try to answer that in reverse. Why was it necessary? So the frequencies of the gravitational waves that nanograv is sensitive to is nanohertz. That's the name. And so those are waves that fluctuate on time scales of basically decades. So you need to measure something like, hundreds of nanosecond time differential over a timing baseline of decades in order to get to that level of sensitivity. Now, it's different from the LIGO detection because they're using a laser interferometer on the ground, and each arm of the interferometer is several kilometers long, and you bounce a laser off of mirrors at the end of these arms. But in a pulsar timing array, you basically effectively sync up a network of pulsars, which act as clocks out in the Milky Way galaxy, and you have each line of sight towards a pulsar is effectively an arm in your interferometer. And what you're measuring are these deviations in the space time between Earth and these pulsars. And you're sensitive to nanohertz frequency waves because you're measuring how these clocks deviate from clock-like behavior on the scale of nanohertz, or hundreds of nanohertz, I should say, over the timing baseline of about a decade or several decades.
So this research involved 15 years of data collection. Mm-hmm. What was the reason behind this? Because it's very long.
Yeah, so it's related to my previous answer, but basically the signals that we're trying, the initial signal that we have evidence for now is basically from the superposition of very many coalescing supermassive binary black holes. And the expected amplitude of those gravitational waves is of order 10 to the minus 15, thereabouts. And in order to get down to that level of sensitivity, again, you need to measure deviations in time of order hundreds of nanoseconds, and then divided by some timing baseline. And that baseline is roughly 15 years or 20 years or 10 years, depends on the sensitivity of your pulsars and so on.
When did you join, and how did you contribute to this collaboration?
Yeah, so I first joined the collaboration in 2009. I was a first-year graduate student at the University of Virginia, and I was already involved in radio pulsar observations. But for a long time, I'd known I was very interested in gravitational wave astrophysics and supermassive black holes, and it just so happened that there was an intersection at my interest at this point, and that was nanograv. So I began by contributing, as graduate students do, looking at the raw data, also collecting the raw data from our telescopes, which are the 100-meter Green Bank telescope in West Virginia and the 300-meter dish, which is no longer in existence at Arecibo in Puerto Rico, and more recently, data from the Very Large Array in New Mexico. So, making observations, contributing to proposals, doing data analysis, modeling the timing for these pulsars. But later in my PhD work, I was involved in developing a new set of analyses techniques to better leverage our data and to ultimately become more sensitive to gravitational waves. After I graduated, I started a postdoc in Columbia, and then I moved to ELTE, where I continued this research. And here I helped put together one whole set of our previous data set, the 12.5-year data set, from which we initially found evidence for these gravitational waves, but we couldn't be certain that they were gravitational waves at that time. But our more recent set of publications and this more recent data set, the 15-year data set, has very strong evidence for the smoking gun signal for gravitational waves.
How did you find ELTE?
Yeah, great question. So I was, it's sort of a long winding story, but I was an undergraduate at Columbia University. I had a set of professors there who were all, they were both of Hungarian origin. So I was first aware of the sort of physics scene in Hungary through these two professors at Columbia. And at that time, actually, Professor Frei Péter was a postdoc there in the research group of one of my professors. So we didn't know each other at the time, but I was aware of his existence as an undergraduate, and he was a postdoc at the time. And this was a LIGO group at Columbia. So I was aware that, that there were LIGO researchers in the United States from Hungary. And then later, as I was doing my own PhD work and then postdoctoral work at Columbia, I was aware that, Péter had gone back to ELTE, and my other professor who had some connections with the university here as well. And then when I decided for other reasons to come to Hungary, I looked up the Astrophysics research group, and I thought to myself, this is a great place to continue my career. And there was a well-established research group in gravitational wave astrophysics, and I could bring my own expertise into the group.
Because we are now discussing ELTE, my question is, how is this research connected to your group?
As Tim said, we have an astrophysics research group, which we usually call Extragalactic Astrophysics Research Group, because we are all interested in extragalactic topics within astrophysics. The source, the gravitational waves, are definitely extragalactic. What they use are pulsars, which are within the galaxy. So in this respect, we should call this as an extragalactic research as well. And the next step will definitely be observing directly mergers of supermassive black holes, which are obviously extragalactic, perhaps in a decade or so, with a space-based observatory with million kilometers of arms, which are suitable for this very slow systems with very long wavelengths and very long time bases. And so part of the extragalactic research group are some people who are focusing on gravitational waves, and we are happy to not just participate in LIGO, but have Tim here who represents us in Nanograph.
Tim, did you face any challenges during your research?
Absolutely. I mean, if you don't face challenges in research, then you're probably not doing it properly. But
Thank you for that.
Of course. Let's see. I suppose some of the more interesting challenges to talk about are kind of sustaining the experiment, because this is a long-term experiment, as you pointed out, and I'm sure many PhD students are aware of, like, okay, I need to get some paper out, I need some exciting scientific discovery or something, bite-sized to do in the next 2 or 3 years, and for something like nanograv, it's you may not get to that initial super exciting result from gravitational wave physics until 15 years. So the question is, like, how do you make a meaningful contribution along the way? And the really cool thing about pulsars is there's so much other science you can do, astrophysics, as you are accumulating the data. So some of the challenges I faced were basically like how to keep myself really interested in this experiment, because early on, nobody had an idea for sure that we could even do it. There were a lot of skeptics, and we continually had to kind of reinvent our sales pitch, if you will. Like, how are we going to convince everybody that we can do this? You should fund us, give us telescope time, and so on. And so that was kind of a perpetual challenge, not just for me, but really for the collaboration. But at the same time, many of us in the collaboration are at heart, first and foremost, pulsar astronomers. And so we loved all the data we were getting, because we could study these things and do other things with them as well. So that's maybe more the interesting challenges to talk about. Of course, they're the more boring challenges of, like, how do I connect with my collaborators? They're all around the world. How do I, like, stay relevant?
And you needed to work with big data, I assume. So
yeah, big data it depends on how you define big data nowadays. Yeah. I'm losing track of what it means to be big data, but we collect data from several first-class radio telescopes in the world, and that's very exciting. And that poses a lot of challenges in and of itself, because the data are not clean. We change instruments every so often, and there are lots of tiny little details to get this right. And unlike LIGO, which faces a completely different set of challenges, it's much more experimental physics when it comes to their detector. Right, we are in observational science, the way that we made our detection, and this was part of the challenging sales pitch to NSF, the National Science Foundation, when we were first established as a physics frontier center. We were like, this is a physics experiment, but we don't have the same control over our detector as, let's say, LIGO does. Our pulsars are hundreds of light years away, and we can't go there. We can't fix them. We can't upgrade them or anything like that. We can only choose the best ones, the best clocks for our experiment. So those are some of the, like, sort of more detailed science challenges.
How many pulsars did you use in this?
Yeah, in this experiment, we timed 68. Mm-hmm. Yeah, 68 pulsars. I should add, though, at this point, that nanograv was not the only pulsar timing array PTA experiment to announce this sort of evidence in this month. So there are at least four other collaborations around the world that form the International Pulsar Timing Array. In fact, in Europe, there's the European Pulsar Timing Array as well, that uses a network of, I believe, 5 radio telescopes to do a very similar thing, using similar pulsars or many overlapping pulsars. But in the Southern Hemisphere, at the Parkes Pulsar Timing Array, they use all the Southern Hemisphere pulsars to make the same set of measurements.
What do you find the most exciting about these new results?
Yeah, so I think what I find most exciting about these new results is sort of two-pronged. One of them is undoubtedly some sort of self-centered selfishness about it, because there are only a certain number of times in the course of astronomical history where you do something like this. So Galileo first used an instrument, a telescope, to observe the stars and the heavens and the planets. in the optical part of the electromagnetic spectrum. And that carried on for some hundreds of years. And arguably, the next part of the electromagnetic spectrum that was opened up to astronomy was radio astronomy via Carl Jansky's initial observations. And then we had X-ray, gamma ray, infrared, UV telescopes, later on in the 20th century. But only with the initial LIGO discovery did we crack open the gravitational wave part of the universe. There's also, high particle astrophysics is also interesting from this perspective, which we haven't touched on at all, and we probably won't go there. But the gravitational wave part of the universe is another way that we just make fundamental observations about what happens across the cosmos. And LIGO is the first collaboration to make detections in one part of the gravitational wave spectrum, and that's up at hertz to hundreds of hertz, right? Yeah. But nanograv and these other PTA experiments have now opened up, in analogy to what I just said with optical and radio part of the electromagnetic spectrum, they have opened up the low frequency part of the gravitational wave spectrum. And so this is the first time we've made observations of this part of this part of the gravitational wave spectrum, basically a new window onto the universe from which we can learn more things. And namely, one of the things that we can learn about is hierarchical galaxy formation. So how did the galaxies that we see come to be? How did they come to be the set of sizes? How did these supermassive black holes get to be the sizes that they are? So that is very exciting. The other part that is very exciting is those sorts of things that we can learn besides what I just mentioned. Years down the road, we also expect to make detections of individual coalescing supermassive binary black holes, but also potentially signals from the very early universe and perhaps new physics from the very early universe. And we think of cosmology nowadays as a very high precision science, and it is, but we're kind of, in a way, up against a wall in terms of the electromagnetic spectrum and what we can learn from that. So if we can learn about the very early universe by other means, namely gravitational waves and some other ways, then we're really going to get more to the heart of the matter of what happened at that time.
I have a very interesting question to Tim about this. He just mentioned about the gravitational waves coming from the very early universe. It's kind of a stochastic background, such as the background of the supermassive binaries. How do you distinguish between the two?
This is a challenging question. It's not exactly my wheelhouse, but so basically the characteristic shape and amplitude of the signals are expected to be very different. So you'll require very strong signals of both to differentiate them and long timing baselines. But one of the ways you would see both is the fact that the two signals are quite different in their spectral content across the gravitational wave spectrum. But yeah, it would almost certainly be these gravitational waves from the earlier universe would be a stochastic noisy signal, just like the one that we have evidence for now. But the other thing is we hope, as we collect more and more data over the years from more and more pulsars, and we do this joint experiment with the International Pulsar Timing Array, that background will become more anisotropic. So in analogy to the cosmic microwave background, when Penzias and Wilson first made those initial measurements, that was basically just a single background with one temperature. And then as the experiments evolved and we had WMAP, what was the predecessor to WMAP?
Colby.
There it is. Thank you. The level of precision on the background and the deviations in the background that you can measure became more and more precise, and then you can remove that from your map of the microwave background of the universe, and then see other things as well. So as we gather more data, we should be able to identify the very loudest sources of nanohertz gravitational waves, and then remove the background and perhaps see something even fainter and something potentially more interesting.
So as a closing question, really, what opportunities are waiting for students here at ELTE in the field of astrophysics?
This question was answered by Tim basically.
Yes.
Recently. We have a research group which is involved in very interesting research topics which are currently at the forefront of science. And we participate in large international collaborations where these things are happening. And we send students abroad, not just students, but later our students become postdocs and they go abroad. But even undergraduate students, both bachelor and master students, participate in these collaborations and frequently travel to sites to collect data, to do whatever Justin described as students or graduate students do. And we have one student who did the BS and MS studies here in Budapest, completed his PhD in Montana in another LIGO group, and then joined the University of Oregon, where they participate in nanograph. And now he's part of the same publication as Tim is. Tim with the Ötvös affiliation and Bence Bécsi as the University of Oregon author on that paper. Is it the State University of the University of Oregon?
Oregon State.
Oregon State. So sorry.
Oregon State University.
There are two different universities.
In Corvallis.
Yes.
And so Bence actually led one of the papers. So he and Neil Cornish, who's also dual LIGO nanograph member, developed some techniques for searching for the continuous wave sources, these individual supermassive binary black hole sources, which will be the next frontier in our science. So it's
Neil
very
Cornish
exciting.
was the supervisor of his PhD work at Montana.
Yes.
And Peter Raffai, whom you already mentioned, previous postdoc at Columbia, returned to Budapest. Right now, an assistant professor here, was the leader of his work, both for the bachelor's and the master's thesis.
Professor Frei and we first met at... I was not at the LIGO meeting, but he and Professor Raffai were at the LIGO meeting in Pasadena at Caltech, and just so happened that Nanograph was having also a meeting that week in Pasadena. We were at, I think, also Caltech. Maybe the LIGO meeting was elsewhere, but also in Pasadena. So having crossed roads at this meeting, we shook hands, and that's how I really got to be aware of the group here. So yeah, it was sort of, this happens a lot in science and the relatively small communities of astrophysics and gravitational wave astrophysics. So yeah, all roads lead here.
All roads lead to Rome, in this case Budapest.
And also ELTE, yes.
Thank you for the great talk, and thanks for the audience for joining us. See you next time. Bye.
Bye.
Bye-bye.